Black holes have the intriguing property of acting as natural time machines due to their immense gravitational fields. This phenomenon is a direct consequence of the theory of General Relativity, which describes how mass warps space-time. In a strong gravitational field like a black hole, time dilation occurs. The closer an object is to the event horizon, the slower time passes to an observer at a safe distance. This effect means that if an astronaut approaches the event horizon of a black hole, their clock, biological or mechanical, will tick slower than clocks farther away from the black hole. Upon returning from this region, the astronaut will find that much more time has passed in the rest of the universe, effectively traveling into the future. This time dilation near the event horizon is a compelling concept, but due to the extreme conditions near a black hole, it is practically impossible for humans to use for time travel. Quasars are among the brightest objects in the universe, and their extraordinary brightness is primarily due to the presence of supermassive black holes, SMBHs, at their centers. These black holes, which have masses ranging from millions to billions of times that of our Sun, accrete matter at high speeds. As the infalling matter accelerates and heats up, it emits enormous amounts of electromagnetic radiation, making quasars visible at cosmic distances. The energy output of quasars can outshine entire galaxies, evidence of the efficiency of the accretion process around SMBHs. This process not only explains their brightness, but also contributes significantly to our understanding of galaxy formation and evolution, since feedback from quasars can affect star formation rates and the interstellar medium. The hypothesis that dark matter can exist in both matter and antimatter forms, and that it can accrete inside dense stars to form black holes, is intriguing. While the nature of dark matter remains unclear, its gravitational effects, such as its role in galaxy rotation curves and cosmic structure formation, are well documented. If dark matter can form black holes, this would suggest new pathways for black hole formation beyond traditional stellar collapse. This idea also aligns with ongoing research on possible interactions between dark matter and baryonic matter, and how these interactions might affect cosmic evolution. The ultimate fate of the universe has long been a subject of study, primarily oscillating between the Big Freeze and Big Crunch scenarios. The Big Crunch assumes that the expansion of the universe will eventually stop and reverse, leading to a gravitational collapse. All matter and energy will merge, resulting in a singularity or something similar to the Big Bang, but in reverse. This outcome depends heavily on the density of the universe and the nature of dark energy. In contrast, the Big Freeze envisions a universe that will continue to expand forever. As galaxies move farther apart, star formation will cease, existing stars will burn out, and the universe will gradually cool down to absolute zero. This scenario is consistent with current observations that suggest that dark energy, which drives the accelerating expansion of the universe, will dominate its fate. Recent research showing that dark matter is being consumed by dark energy suggests a new dynamic in our understanding of the composition of the universe. The idea that dark matter and dark energy may interact opens up several theoretical possibilities. For example, if the driving force of dark energy is increasing, it could lead to scenarios in which the fabric of space-time itself changes, affecting the distribution and behavior of dark matter. The asymmetry between the masses of protons and electrons can be understood through Planck's distribution law, particularly in how energy is distributed at different temperatures. This asymmetry affects the frequencies of electromagnetic radiation and strengthens the implications for the annihilation probabilities of matter and antimatter. The notion that dark energy and dark matter could arise from these compensatory asymmetries is speculative, but offers an interesting perspective for further theoretical investigation. The connections between black holes, quasars, dark matter, dark energy, and the fate of the universe paint a picture of a cosmos that is as dynamic as it is mysterious. Each element, whether it's the time dilation properties of black holes or the bright signals of quasars, contributes to our broader understanding of astrophysical phenomena and the fundamental forces that shape our universe. Quasars, one of the brightest objects in the universe, can be seen from billions of light years away due to their extraordinary energy output. This tremendous brightness is primarily attributed to the supermassive black holes, SMBHs, at the centers of quasars. The energetic radiation from quasars is a result of accretion disks surrounding these SMBHs. As matter spirals toward the black hole, it forms an accretion disk where friction and gravitational forces heat the material to high temperatures, resulting in a significant release of energy. This process converts some of the rest mass energy of the infalling matter into radiation, as described in Einstein's energy mass equation. The existence of SMBHs is inferred from the electromagnetic radiation emitted by these hot accretion disks, which range from visible light to X-rays. By analyzing this radiation, scientists can determine the mass of the black hole. Black holes have a growth limit known as the Eddington limit, which balances the gravitational force on the accreting material with the outward radiation pressure from the accreting disk. However, SMBHs observed in the first 500 million years after the Big Bang exceed this limit, suggesting alternative growth mechanisms. Tal Alexander and Priyamvada Natarajan proposed a mechanism for super Eddington accretion that explains the rapid growth of early SMBHs. In the early universe, the first star clusters were likely gas-rich, allowing light black hole seeds, 110 solar masses, to efficiently accumulate mass through interactions with dense cold gas and massive stars. This process involves the black hole sweeping up the gas in a wind-like manner rather than forming a traditional accretion disk. Their calculations show that this geometry allows accretion rates that exceed the Eddington limit, providing a plausible explanation for the formation of early quasars and the rapid growth of SMBHs. A recent hypothesis suggests that dark matter, potentially made up of both matter and antimatter, could accumulate in dense stars, causing them to collapse into black holes. This idea offers an explanation for the missing pulsar problem at the center of the Milky Way, where fewer pulsars than expected have been observed. The researchers suggest that asymmetric dark matter could accumulate in pulsars, causing them to collapse into black holes. The asymmetric dark matter model proposes that dark matter comes in two varieties, matter and antimatter. Unlike regular WIMPs, weakly interacting massive particles, which annihilate on contact, asymmetric dark matter particles of the same type would not annihilate each other, allowing them to accumulate inside stars. In dense environments such as pulsars, this accumulation could lead to the formation of small black holes. If this scenario holds, pulsars near the galactic center, where the density of dark matter is highest, would have shorter lifespans due to their rapid collapse into black holes. This relationship between pulsar age and distance from the galactic center may provide indirect evidence for asymmetric dark matter. For much of modern cosmological history, two main theories have been proposed to explain the ultimate fate of the universe: the Big Freeze and the Big Crunch. This theory posits that the expansion of the universe will eventually slow down and reverse, leading to a gravitational collapse in which all matter and energy are pulled into a single point. This cataclysmic event is essentially the reverse of the Big Bang, causing the cosmos to collapse. In contrast, the Big Freeze envisions a universe that will continue to expand forever. As galaxies move farther apart, star formation stops, existing stars burn out, and the universe cools to absolute zero, becoming a cold, dark wasteland. Edwin Hubble's observations revealed that the universe is expanding, with distant galaxies receding faster than nearby ones. This discovery was later developed through the study of type Ia supernovas. These supernovas serve as standard candles because of their consistent intrinsic brightness, allowing astronomers to accurately measure cosmic distances. By comparing the observed brightness of these supernovas with their expected brightness, scientists have determined the rate of expansion of the universe. As light from distant galaxies travels toward Earth, it experiences a redshift to longer wavelengths due to the expanding universe. The degree of redshift is related to the rate at which these galaxies are receding, confirming the accelerating expansion. This phenomenon, which has been meticulously observed over many years, supports the idea that not only is the universe expanding, but that this expansion is accelerating. The accelerating expansion of the universe implies the existence of a repulsive force that we call dark energy. Observations from the Planck satellite and the Wilkinson microwave anisotropy probe, WMAP, provide strong evidence for a flat universe, suggesting that dark energy makes up about 73% of the total energy density of the universe. Dark matter and baryonic matter make up the remaining 27%. The Wigglesy Galaxy Survey, which observed over 200,000 galaxies, further supported the existence of dark energy by analyzing baryonic acoustic oscillations and redshifts. This research strengthened the dark energy hypothesis by determining that the expansion of the universe accelerated around 7 billion years ago. The simplest explanation for dark energy is Einstein's cosmological constant, which represents the vacuum energy density of space. This constant exerts a negative pressure that accelerates the expansion of the universe. Similar to the Casimir effect from virtual particles in a vacuum, the cosmological constant accumulates to drive the accelerated expansion of the universe. Despite the theoretical elegance of the cosmological constant, inconsistencies have emerged. Pan-STARRS observations of type Ia supernovae suggested a value for the dark energy equation parameter that deviates from the expected -1, potentially invalidating the simplest dark energy model. Recent research from the universities of Portsmouth and Rome suggests an interaction between dark matter and dark energy. This model suggests that dark energy is not static, but grows over time, consuming dark matter and slowing the growth of cosmic structures. This dynamic interaction could provide a more detailed understanding of cosmic evolution and the observed acceleration of the universe. The observed expansion of the universe has long been a cornerstone of cosmological models, particularly the Big Bang theory. Measuring the rate of expansion of the universe, particularly through observations of redshift, suggests that the universe is very close to a critical density. This density is the threshold at which the universe will eventually slow its expansion and collapse inward, leading to the Big Crunch. Since the 1990s, type Ia supernovae have provided a consistent method for measuring large cosmic distances. By comparing the apparent brightness of a supernova to its known intrinsic brightness, astronomers can accurately determine its distance. This method has been crucial in establishing that the rate of expansion of the universe is accelerating. The accelerating expansion of the universe was first suggested by observations of distant type Ia supernovae, which appear dimmer than would be expected for a slowing universe. This meant that these supernovae were further away than their redshifts would suggest under a constant or slowing expansion model. These findings pointed to an unknown energy density that opposes gravity and drives acceleration, now called dark energy. Einstein's field equation includes the cosmological constant, which can be interpreted as a vacuum energy density. When this constant is positive, it contributes to the observed accelerated expansion. A positive vacuum energy density causes negative pressure, which drives the accelerated expansion of the universe. Several models attempt to explain accelerated expansion with the central concept of dark energy. Dark energy is characterized by negative pressure and a relatively uniform distribution in space. Although dark matter does not interact with electromagnetic radiation and is invisible, it exerts gravitational effects that affect visible matter and the large-scale structure of the universe. According to the Planck mission, the total mass energy of the universe is composed of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. This composition suggests that dark matter makes up about 84.5% of the total matter, while dark energy and dark matter together make up 95.1% of the universe. The CMB is the thermal radiation left over from the Big Bang and provides a snapshot of the early universe. When the universe cooled enough for protons and electrons to form neutral atoms, the CMB was released and the universe became transparent. The uniformity and small fluctuations of the CMB were crucial to understanding the early conditions of the universe and its subsequent evolution. Thermal radiation, produced by the thermal motion of charged particles, covers a broad spectrum of electromagnetic radiation. All matter above absolute zero emits thermal radiation, and the spectrum reflects the various energies and accelerations of the particles. The accelerating expansion of the universe driven by dark energy has profound implications for cosmology. The precise nature of dark energy remains one of the most important questions in physics. While the lambda CDM model provides a solid framework, inconsistencies in observations, such as those identified in the Pan-STAR survey, indicate the need for further research and potential refinement of existing models. In classical physics, electrons in a steady current create a decreasing charge distribution along the wire, producing a vector potential experienced by electrons in relative motion along the wire. This charge distribution helps us understand electromagnetic fields and waves resulting from self-sustaining electric currents. Accelerated electrons produce electromagnetic waves that travel at the speed of light. One of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle, which is closely related to the intrinsic acceleration of particles. The concept of particle-wave duality, in which particles exhibit both particle-like and wave-like properties, can be seen through the lens of accelerated motion and diffraction patterns. Planck's distribution law, which describes the energy distribution of electromagnetic radiation, supports this duality and helps understand the behavior of particles at quantum scales. Lorentz transformations, derived from the Michelson-Morley experiment, provide a practical method for transforming time and geometric coordinates. They are based on the behavior of light and the relative motion of observers. The mystery of how accelerating charges maintain a force that is locally accelerated by the charge distribution is explained by recognizing that charges and electric fields are two aspects of the same phenomenon. This duality prevents charges from exceeding the speed of light. Relativistic mass change is explained by electromagnetic induction. As the acceleration of the charges changes, an inductive electric force opposes this acceleration and causes a change in mass. This explains why mass increases with speed, increased relative mass, and decreases with slowing down. This relationship shows that the mass of particles such as protons and electrons is related to their electromagnetic properties and the frequency of their associated waves. Electromagnetic inertia is caused by the negative electric field created by changing acceleration, magnetic induction. This concept leads to the idea that mass is electromagnetic. The different frequencies of the proton and electron, as explained by Planck's dispersion law, explain their different masses and the wavelengths of their diffraction patterns. If the mass is fundamentally electromagnetic, then gravitational forces can also be electromagnetic. Charges moving in parallel attract each other via magnetic effects. This concept is compatible with the idea that gravity is an electromagnetic effect caused by the accelerating universe. The graviton, a hypothetical massless spin 2 boson, mediates gravitational forces in quantum field theory. Its existence explains how gravitational forces operate at the quantum level, interacting with the stress-energy tensor in a way consistent with general relativity. The discovery of a gravitational free spin 2 particle would provide direct evidence for gravitons. The idea that accelerating charges and their electromagnetic fields are integral particles for understanding both inertia and gravity suggests a unified theory. The Planck distribution law's explanation of frequency-dependent mass and the electron-proton mass ratio offers a path to such a theory. The intrinsic acceleration basis of quantum theory is evident in phenomena such as the Heisenberg uncertainty principle and particle-wave duality. The changes in mass with speed are due to electromagnetic induction, which relates mass to the frequency of electromagnetic waves. The forces of mass and gravity may be electromagnetic, influenced by the accelerating universe. The hypothesized graviton would explain gravity at the quantum level by unifying quantum mechanics and general relativity. The interaction between electromagnetic fields, intrinsic acceleration, and quantum phenomena suggests a potential unified theory of electromagnetism and gravity. Ultimately, the discovery of accelerating electrons, electromagnetic fields, and intrinsic acceleration offers profound insights into quantum mechanics and relativity, pointing to a unified understanding of mass, inertia, and gravity. This framework not only reconciles classical and quantum physics, but also paves the way for future discoveries in the fundamental nature of the universe. Thanks for listening. Take care.